there's something weird in this formula for finding fractal dimension. The fact that you have to take the negative of the output to get the correct dimension is very strange, because the source of that is the scalar value of f, or epsilon. I'm using f because it makes more sense. It's easier. I can write it on the computer, right? I don't have an epsilon key. I have an f key, and it's a scaling factor, so that makes sense. So notice something here. If I take the natural logarithm of 3, I get this. Let's put that into our memory number. Clear that out. If I take the logarithm, or the natural logarithm of the inverse of 3, I just get the negative of that same number. So right, if I add this to our memory number, I'll recall the memory number. Look at that. It's exactly the same, it just has a different sign. They add together to give us nothing. So what we could do for the Koch snowflake is we can take n is 4, take the natural log of that. Let's clear our memory number, save this into it. All clear. Now we'll just take, we're dividing by 3 constantly, right? Where we should get 3, right? So just take that. Now let's take the inverse of this and multiply it by our memory number. There we go. Now our dimensionality is the correct sign. So we can actually clean up this equation and make it less stupid if we are just less stupid. So now n doesn't change. N is this is how many units we're using, and f is how many units we predict we should use. That's what the 3 now means, instead of being some weird thing that we're dividing by that doesn't make any sense. F actually makes more sense now, or epsilon makes more sense now, and n makes more sense with respect to it. And you don't end up having to take the negative of your dimension to get the correct dimension. This is the power of dimensional analysis right here, right? When you think it through, your units should make sense, right? But the way that this equation was first formulated, there's weirdness to it. Like there's things in it that just are very strange. And the reason for that is it was put together without any attention paid to dimensional analysis. Right? So when you come across like engineers and whatever the fuck, and they're like, oh, you can't always trust dimensional analysis. Yeah, you actually can. Dimensional analysis is the only thing you can trust, right? Because math, if you're just treating it as math operates over numbers, it can tell you fucking anything. And it doesn't make any sense necessarily, right? And that's, I think, fundamentally, that's one of the main issues with quantum mechanics right now. It's the sort of shut up and compute ideology rooted in the notion that math is about numbers. No, you need the dimensions to always make sense. And when you get it so that all of the dimensions make sense everywhere, your formulas became far, far simpler. They're more intuitive, they're easier to work with, they're easier to derive. If you kind of get lost and forget, like, you know, memorizing equations and formulas, that's kind of dumb. If you understand the problem, you should be able to derive your formulas and equations just pretty much off the top of your head, because the dimensions need to make sense, right? So here, you know, let's clear this, right? So say we had something analogous to a Koch snowflake, but instead of gaining 4 pieces for every what should be 3, we gain 5, right? So let's do that. Let's see what that looks like, right? So ln of 5. Let's store that. All clear. And what we expect is it should be 3, right? So let's take that. And then we're going to divide by this. This is our denominator here. So we're going to take the inverse of that and multiply it by our memory number. And the dimension of this is 1.46497352. Lovely. Slightly higher. Right? What do we need to do to get to 2? Well, probably 9. Oh, look at that. Yep, that's how hard this is. Oh my god.